We are now going to use power functions to help us determine the end behavior of a general graph. And so the important thing to recognize here is we're going to start with just the end behavior as our first step. And then from there, we're going to determine what that means. And so here's just a little bit of notation we want to talk about. We're going to talk about how y changes, y equals f of x, as x. This will approach either infinity or negative infinity as x approaches infinity or negative infinity. So the way this reads is that our y value or our f of x value approaches either positive infinity or negative infinity as x approaches infinity or negative infinity. So if I write y approaches infinity as x approaches negative infinity, this is what it means. If I'm looking at my graph, it means that on this side I'm going, as x approaches negative infinity, y is going up, so my graph is doing this. But if I write y is approaching infinity as x approaches infinity, then here's my x approaching infinity, here's my y approaching infinity, and my graph is doing this. So it's a shorthand notation way of writing what y is doing as x is doing something. And notice that we care about the infinities here because we care only about the end behavior. How does it appear on the edge or the end of our graphs? And so here's a table that you'll need to keep track of, and this will be in the handout section of the website. But with this graph, what it's telling us is that if we look at the leading coefficient a, and then we look at the degree n, then we've got an n is even case and an n is odd case. And for the even case, if a is positive, then it's going up in both directions. Y is approaching infinity as x approaches infinity and as it approaches negative infinity. So this is like our x squared graph. If it's negative, then it means it's going down instead. That's just being reflected over the x-axis. Well, if it's odd, we still have a positive negative, but here's the key. Notice that if it's positive a, then it's positive here, and it's negative here. But if it's a negative a, then it's positive on the left and negative on the right. So the real rule here is that the end behavior is this on the right side is the same as a. It's the same sign as a. So if a is positive, then the right side is positive. If a is negative, then the right side is negative. And then, if it's even, the left is the same. And if it's odd, then the left is the opposite. And that's how we can quickly determine our end behavior. So let's look at a function. Let's say p of x equals 4x cubed plus 2x squared plus 5x minus 17. And what we want to talk about is the fact that this isn't a power function, but the end behavior all relies off of this term right here. Because as x gets larger and larger, this term becomes more and more important. And the way we can show this is if we factor out an x cubed, and that sounds funny because it's a little too big, but if we pull an x cubed out of this, that's going to leave 4 plus 2 divided by x plus 5 divided by x squared minus 17 divided by x cubed. And as I let x get bigger and bigger and bigger, these numbers get smaller and smaller and smaller because their bottoms get bigger. So they contribute less and less and less to what this one does. So all we care about is the 4x cubed term. So the power function for 4x cubed tells us that it's a is equal to 4 and the degree is 3, so it's odd. So we know that on the right side it's the same as a, so the right side is positive. The left side, since d is odd, our degree is odd, then it's the opposite. So it's negative. So if I were to look at a graph of 4x cubed plus 2x squared plus 5x minus 17, it would be going up here and it would be going down here. And that's how we can determine end behavior from the function by just looking at the lead term. That's why the lead term is so important.